All right, hello everyone. This is going to be a pretty fast review lesson on determining where a function increases and decreases and determining where the function is concave up and concave down. I'm only going to do 2 examples. If you need more, there are more in the videos below, but this is another major topic from Calc AB, so we're just trying to review it now so that we can utilize it for future things. So, first example I want to do is I give you a function like one of these ones. I'm going to start with a little more complicated one. And I'm going to go through the entire thing. I'm going to find the intervals where the function's increasing and decreasing and where the function is concave up and concave down. If you forgot what concavity is, go watch the old videos. If you forgot what increasing and decreasing is, go watch the old videos. But again, major topic in AB, so let's just get to it. So to find where a function is increasing and decreasing, we start by finding the critical points, or where the function has a horizontal tangent, or where a function has relative maxes and mins. All of those are the same thing. So we take the derivative to do that. Derivative of the first, which is a chain rule, so times 3, because it's the chain rule, times x plus 2, original second, plus derivative of the second, which is 1, times original first. Okay, at this point, if you try to multiply it all together, you're wrong, because you're not going to be able to solve it that way, because there's cubic terms in here still. So the best way to do it is, this is one of the problems I love to do last year, factor out whatever is in common. Oops, I missed a 3 here. Sorry. So factor out whatever is in common. So notice there's a 3x minus 1 squared, a 3x minus 1 cubed. So I can take the 3x minus 1 squared, factored out of this term, and I'm left with a 3 and a 3, so 9 times an x plus 2. Plus, I took a 3x minus 1 squared out, so I'm left with just a 3x minus 1. This should happen in these types of problems where you're left with 2 factors. One will be a squared factor, and then we can reduce this one down. 9x plus 3x is 12x. 18 minus 1 is 17, so 12x plus 17. Interesting. 12x plus 17, right? 3x minus 1 squared, 9x plus 3x is 12x, 9 times 2. Yeah, it's weird I have a different value here. Anyway, 12x plus 17. Okay. At this point, and we'll check our answer Desmos, maybe I messed something up, but I don't think so. You set each factor equal to 0 to find the horizontal tangents, aka the critical points, aka the location of possible relative maxes and relative mins. So in the first one, we get an x value of a third. In the second one, we get a value of negative 17 over 12. So then you make your number line from negative 17 over 12, 1/3, and we label our number line, and then we test points in each interval to determine where the function is increasing and decreasing, and then I'll also determine if these are relative maxes or relative mins. So remember, we plug into the derivative. We don't plug into the original, we plug into the derivative. So I'm going to start with something bigger than 1/3, like 10, positive, positive, so positive. Let's plug in 0, negative squared. So this term's always positive, so I really don't even need to think about that. When I plug 0 in here, I'm also positive. When I plug in a negative 10 here, that's the negative. So I know this function, if I were to try to do a little curve sketch, decreased, hit its min, increased, leveled out, and then went up some more. So this is a relative min. This 1/3 is a neither. It's not a relative max or a relative min. It is a critical point, probably be an inflection point, but it is not a relative max or relative min. Okay, from here, I have my first derivative. Now I'm going to find the second derivative. So take the second derivative, which says derivative of the first. I keep doing that, times 3, times the derivative of the inside, times the original second, plus derivative of the second, which is a 12, times original first. And we can do the trick one more time where I factor out what's in common. There is a 3x minus 1 in common again, which I'm going to take that out. I'm going to leave over the 2 times 3, which is 6 times 12x plus 17, plus I have a 12 times a 3x minus 1. And that gives me 3x minus 1 times 6 times 12, 72x plus 36x, 108x, hopefully. 6 times 17 is 102. Minus 12 is 90. I did that kind of fast. Hope I didn't make a mistake. And then that gives us 2 inflection points where the graph changes concavity. And negative 90 over 108. That's exciting. And then same deal. You make your number line, and this is where you find the intervals where the function is concave up or concave down. So negative 90 over 108 and 130. Let's plug in 0. We get a positive times a negative is negative. And when you're doing these problems, you're never going to have 2 negative intervals next to each other unless there's a cusp or something. So I already know these are going to be positive. We always change concavity at inflection points. Unless there's a cusp, but this function is differential. There's no way. Think about it. Like, you can't, do I have room under here? You can't change, or you can't maintain concavity if the second derivative is like, it just doesn't work. You have to change concavity at an inflection point if the function is differentiable. So we have our 2 inflection points. We are concave up from negative infinity to negative 90 over 108. We are concave down from this interval, and then we are concave up from 1/3 on. Let's check it just with Desmos, because for some reason I have a different answer than what I have in my notes, and that's curious to me. So if we graph it, we have 3x minus 1 to the 3rd and times x plus 2. So it's a 4th degree. There it is. Goes all the way down, 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 very steep down to whatever this point is, negative 1.417, which is probably negative 17 over 12. Yeah. And then we go up, 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 up until we have our nice little critical point at 1/3, which is what we said, and then it continues going up. So that looks good. Overall, I think that's good. If I made an error with my inflection points, you can tell me about it in class. But the idea is you need to be able to find the intervals where we are increasing and decreasing, and find the intervals where we're concave up and concave down. All right, let's do one more. Another common problem I like. We're going to see these with trig. We'll do a lot of those in class and assessments because we are working through trig. But the other ones that are fairly common that we want to start handling are functions like this that have e to the x in them. So same deal. Let's find the intervals where the function's increasing, decreasing. And then I might not even do concavity for this one because it's the same process. So let's find the first derivative and just remind you of a few things. First derivative of this, derivative of the first times original second, plus derivative of the second, which is just e to the x, times original first. So there's my derivative. Now, one of the best strategies when you're trying to solve something like this, you need to factor. Find the common factor, which is a 3 e to the x. What you are left with is a 1 plus x. Set each piece equal to 0. And then what you really need to remember, and why we're bringing this up, is 3 e to the x equals 0 has no solutions. E to the x never equals 0. E to the x is always a positive value. So there are no solutions from this piece, which means there's only one critical point at negative 1. So make our number line negative 1. Label your number line. And plug in something bigger than negative 1, like 0. We get a positive times a positive. Like I said, this is always positive, so we have positive. And then we plug in negative 2, we get a negative. So this graph decreases, levels out, and increases. That means this point right here is a relative min. So we come back to Desmos. We can check this one and see how we did. 3x b to the x. And look at it. Decreases, decreases, decreases. At -1, it begins increasing. So these are typical problems that I like to give because they don't have decimals. You can do them all without a calculator, which is what I like right now. And then if you were to find the second derivative from here, you would just do the product rule. And then you could find where the function was concave up and concave down. From the graph, it looks like it's concave down. It looks like there's an inflection point somewhere in this range. And then it goes concave up the rest of the time. So concave down flips here to concave up, and then it's concave up for the rest of the time. Somewhere in this section, I think. Because look, see how it's speeding up in the negative direction and then slowing down in the negative direction? So that means there has to be an inflection point somewhere. All right, so that's it. The homework deals with this topic. Like I said, if you need more information, there are videos down below. But that's where I'm going to stop. All right, goodbye.